Hi class, welcome to chapter 13 where we're going to talk about vector functions. I want to start in section 13.1 with a real brief introduction to vector function and space curves. I just want to lay the foundational groundwork for this chapter in this lecture. Okay, so in general, a function is a rule that assigns to each element in a domain an element in the range, right? We've learned that from our way pre-calculus math course. So what a vector valued function, or just vector function, both mean the same thing. It's simply a function whose domain is a set of all real numbers and whose range is a set of vectors. So a vector valued function, its range, its output is vectors. So we are most interested in vector functions we'll call R, whose values are three-dimensional vectors. So that's where we're going to be spending most of our time in three-dimensional space. This means that for every real number t that's in the domain of this vector R, there is a unique vector in three dimensions denoted by R. So the vector R is a function of t. So this when you see a bolded R here or a bolded letter here followed by a t, this is telling us it's a vector valued function. Okay, so we have these components, f of t, g of t, and h of t are the components of the vector r of t. Then f, g, and h are real valued functions, and they're called the component functions of r. And this is how we can write it. Our vector value function r of t is equal to our components f of t, g of t, h of t. Or we can write it as f of ti, g of tj, plus h of tk. Both of these are the same. It's fine. So we use the letter t to denote the independent variable because it represents time in most practical applications of all vector valued functions that we'll look at. All right, so let's take an example here. So if we have the vector value function r of t and its components are defined as t cubed plus the natural log of 3 minus t, comma, and the last part is the square root of t. Okay, then what we can see here, these are the individual components of it that I was talking about. All right, so what we know next is the domain of R consists of all values of t for which the expression R of t is defined. So what would be the domain of this vector valued function? All right, well, look at this. This right here can take on all values of t. This can only take on positive values of t, or greater than or equal to 0. But what about here in the natural log? Well, this must be greater than 0, okay, that you can't plug in 0 or negative numbers in the natural log. So the domain is all values for which 3 minus t is greater than 0. Well, that's the case, and going back, sorry, and also t is greater than or equal to 0. So subtracting the t over, you get 3 has to be less than 0, but then it also has to be at the same time greater than or equal to 0. So the domain of this vector valued function is all numbers from 3 inclusive, or excuse me, 0 inclusive to 3. All right, let's talk about limits and continuity. All right, the limit of a vector value function R is defined by taking the limit of its corresponding functions, all right, as follows. So if you have a vector value function and you want to take the limit of this function as t goes to a of the vector valued function, all you do is take the limit as t goes to that value for all of these values. For example, if in here you wanted to look at the limit as t goes to 1, you would just take the limit as t goes to 1 of this, limit as t goes to 1 of this, and the limit as t goes to 1 of this. You know, that limit as t goes to 1 of this would be 1 cubed, this would just be the natural log of 3 minus 1, and this would just be the square root of 1. All right, and this is just provided the limits of the component exist. So really what's going on here is the limit of vector value functions obey the same rules as limits of real valued functions. Nothing is different here. So further application of this formula, a vector function R is continuous at A. Obviously, if the limit as t goes to A of R of t is just equal to R of A, okay? Now let's talk lastly just about space curves here. All right, so there is a close connection between continuous vector function and space curves. So suppose that f, g, and h are continuous real value functions on some interval I. Then the set C of all points in space where x is equal to the first component of that vector value function, y is equal to the second component of that vector value function, and z is equal to the third component of that vector value function. And t varies throughout the interval I. This is called a space curve, okay? So the equations here in 2 are called parametric equations of C, and T is called the parameter. So we can think of C as being traced out by a moving particle whose position at time t is given by those components in the three-dimensional plane. And if we now consider the vector function r of t, then r of t is the position vector of the point p, f of t, g of t, h of t on this plane curve C. And this picture here is kind of showing it, okay? Like suppose you have this curve in space. Okay, and it looks like this. So you can even think about it as this particle is moving along this curve, okay? This specific point here on the curve can be defined as the point f of t, g of t, h of t. This r of t, this is that vector valued function. And what this vector valued function does is it traces along this curve here. And this specific point of the vector value function is just the vector from the origin to that point right there. That's all it is. So this C is traced out by the tip of the moving position vector r of t. That's what we're seeing with this vector valued function. All right, let's just do one quick example so you can see this. Let's sketch the curve whose vector equations are the following. So our vector valued function r of t is cosine of t I sine of tj plus t of k. This is a very common vector valued function. So the parametric equations for this curve are the following. X is equal to cosine of t, y is equal to sine of t, and z is equal to t. All right, so how do we even begin to sketch this? Well, obviously, with just some obvious trig identities here, we see that x squared plus y squared is the same thing as cosine squared of t plus sine squared of t, and that's going to be equal to 1, always, always. So obviously, then the curve must lie in a circular cylinder represented by x squared plus y squared is equal to 1. The point x, y, and z lies directly above the point x, y, 0, which moves counterclockwise around the circle x squared plus y squared is equal to 1 in the xy plane. And this right here shows you that. So this right here is the space curve that we see. And the vector value function emanates at the origin and literally just follows this. This figure is what's called a helix. All right. This corkscrew shape of the helix that we just saw in that example is familiar from its occurrence in coiled springs, and it's also occurs in the model of DNA.